G'day, in this video we're going to dig deeper into looking at how forces act during circular motion. We're continuing to build on our understanding of inquiry question 2, which is why do objects move in circles? We've already been unpacking dot points 1 and 3, which look at being able to measure and describe circular motion. We're also incorporating dot point 2 today, where we analyze forces acting on an object executing uniform circular motion in a variety of situations. And the examples that we're going to be looking at are cars moving around horizontal circular bends, mass on a string, and objects on bank tracks. So our key learning intentions today is to first explore forces which act on a mass on a string and then complete an associated practice problem. We'll also look at forces which act on a car driving on a horizontal bend as well as a bank turn. In particular, we're going to focus on completing a practice problem for the bank turn. So first off, let's look at the concept of mass on a string. A lot of circular motion questions are going to be focused on the concept of having an object moving in a uniform horizontal circular path and achieving this by rotating around a centralized point attached by a string. The string will provide tension which works to oppose the object from flying in an outwards direction, and it's this tension force which keeps the object rotating in its circular path. A lot of the time though, when we have a mass on a string, we'll find that there is some sort of angle theta. And there's a couple of ways that we can express theta. Either we could refer to it as the angle between the radius of the object in the circle and the string itself, or we could also talk about it in terms of the centripetal force and the force of tension on the rope. Effectively here, when we are moving a mass in a circular motion on a string, the string isn't usually parallel with the horizontal surface of the ground. The object in some way is sitting a little bit lower than that central point of rotation, meaning that the rope and thus the tension force is on an angle as well. This angle theta describes this angle. Something else that's important to note is that we can split the tension force which exists on the rope into vertical and horizontal components. Ft sine theta here, or the tension force in the y component, is always going to be equal to negative mg. Essentially, it is the equal but opposite force to mg. We can assume that the value of this force is going to be equal and opposite because we're working with uniform circular motion in which the object will have no vertical displacement, meaning that the tension force in the y component and the force due to gravity need to be balanced, equal but opposite. The other tension component is Ft cos theta, or the tension force in the x component, and this is simply equal to the centripetal force. This is the force which is acting on the object to pull it in back towards the center, so it will follow that uniform circular path. It's a little bit different to other circular motion questions and problems that we have focused on so far, because we've said that the only force that's causing some sort of acceleration. But here we're now adding in this y component of a force. However, the whole point of this force is to simply balance out the force which occurs due to gravity. You may at times see some problems which are very similar to our horizontal mass on a string problem. However, there would be a rotation in which the object is moving in a vertical circle. These problems are a little bit harder to analyze, but there can be some analysis that we do on the object at the top and bottom of flight. As you can see here, when the object is at the top of flight, the tension force and the force due to gravity will be additive with each other. And at this stage in the flight, the object is going to be experiencing a force which is a combination of both. However, when we get to the bottom of the circle, our tension force and our gravity force are working against each other. In our practice question for today, we're going to be focusing on horizontal motion, much more common in the scope of this topic. For our practice problem today, we have an athlete that spins a hammer weighing 7.26 kilos horizontally. While they're spinning the hammer with a radius of 2 meters, the hammer completes 1 revolution every 1.5 seconds. We're being asked to calculate the angle between the hammer's y and the horizontal. So again, what we're expecting is that the hammer is not going to be parallel to the horizontal of the ground when it's being spun. Instead, what we expect to see is that the hammer is sitting on some sort of angle like this, where if we did have the horizontal or a line parallel to it, there would be an angle in between the wire. This is what we're being asked to calculate for in the question. Essentially, this can be determined by doing some vector analysis of our tension, force, and its components. Now, given the diagram, it's going to be probably the most straightforward with the information that we have to calculate first for Ft in the y component, as well as F tension in the x component. If we have those two values, we should be able to calculate for theta using some right-angled trig. However, before we do that, we are going to have to calculate for both of those forces. What I'm going to do first is develop a little bit of a data column. From here, let's identify some relevant formula. Given the formula that we have here, we do have access to most of this data already. Mass, gravity, radius have all been given or could be found in our data sheet. However, we should note that we currently do not have the velocity of the hammer as it's rotating. What this means is this is another value that needs to be calculated. From here, we can substitute and solve. Our final answer here is 16 degrees to two significant figures. As always, it's really important to note that when completing these calculations, we need to be saving the exact values in our calculators at all times, as substituting in rounded errors as we go will lead to rounding errors at the end. Another type of motion we'll be examining in class is a car on a horizontal bend. Now, these forces are quite straightforward to account for. You have the car sitting on a horizontal, which means that you've got mg for gravity and the normal force being equal and opposite in this case. The only thing that's going to make a car move around a horizontal bend is some sort of friction force, which will act essentially as the centripetal force. As such, problems that involve a car moving around a horizontal bend are actually quite straightforward, and all we're required to do is employ some kinematics and dynamics concepts that we learned about in Module 1 and 2, nothing too unfamiliar there, as well as some of the key principles that we've learned with our basic circular motion as well. Where things can become a little bit interesting, though, is if we have a car moving on a banked turn. Now, because the car is traveling on a road that is banked or at an angle, the normal force is now no longer parallel to Fg. As a result, there is an x component force caused by this normal, which results in a net force which moves the car towards the lower part of the embankment. Now, at most speeds when driving around a banked turn like this, you would still need to apply some sort of friction force by using the steering wheel to keep your car traveling in a straight motion. However, if you do drive at the perfect velocity on this bank turn, the generated net force going towards the center will be enough to keep the car traveling around the bank turn perfectly in a stable manner in which you are not moving up the embankment or down the embankment, effectively meaning that no steering is actually required to keep the car in place. This scenario leads to a few mathematical assumptions. So effectively, if the car is not moving up or down the incline as it is moving along the bank turn, again, we've hit that sweet spot for velocity, the assumption that we can make is that the net force vector is going to be equal to the sum of the force for gravity and the normal force. In practice, that looks something like this. We end up with a vector triangle between the three forces where Fg equals mg, the net force is equal to our centripetal force, and the angle between the force of gravity and the normal is equal to theta, the angle of the embankment. These assumptions can be quite helpful in enabling us to complete calculations for turns such as these. In the practice question we have for today, it says that a car which is 1,750 kilos is driving on a road which is banked 15 degrees to the horizontal. We're being asked to calculate the radius of the curve if the car can turn the corner using no friction at 51 kilometers an hour. So if we were to look at a top-down view of this process, we have some sort of curve which is on an embankment and a car which is driving on it. The radius that's being referred to in the question would be the distance between the car and whatever the central point of the curved part of the road is. In other words, if we were to draw this curve around as a full circle, it would be the central point of the circle. Note that in this question it says that the car can turn the corner without using any friction at all, meaning that you're driving at your constant 51 kilometers per hour and you're able to make the turn around the banked curve without using any steering, effectively just driving straight. What I'm going to do first is draw a simple diagram to show a front-on view of what's happening with the car. So in this problem, some key things to acknowledge is that the force due to gravity, as always, is equal to mg. The net force is going to be our centripetal force. We're working on an embankment of 15 degrees. And assuming, as the question says, that the car turns with no friction, then the sum of the gravity and normal forces will be equivalent to the net force, which effectively is our centripetal force. To help solve for this problem, I'm going to draw a diagram that reflects this. Before solving, I'm just going to do a quick data column to extract any data out of the question which we have not collected yet. As always, we can convert speeds in kilometers per hour to meters per second by dividing by 3.6, and that will give us a speed which is approximately 14 meters per second. As always, values like this and any other values that we calculate along the way in our solution need to be saved into our calculator to avoid rounding error. Now that we've extracted all relevant information out of our question, we now need to come up with a method in order to calculate for the radius of this curve. A solution that makes sense given the data that we have is to use our formula for centripetal force. If we rearrange and solve for r, we find that the radius is equal to mv squared on the centripetal force. Now we already have m and v, the only thing that we don't have is centripetal force. However, using some right-angled trigonometry, because it is assumed here that the net force is parallel to the horizontal, therefore it has a right angle between there is a right angle between the Fnet and Fg vector. Some right angle trig can be used to calculate for Fnet. Given that we don't have any information about the hypotenuse, the normal force, what we can do is use our tan formula to solve for Fnet. This comes out to 4,600 newtons to two significant figures. And this value can be substituted directly into our solved formula for r in order to calculate for the radius. And the value that we get is approximately 76 meters to two significant figures. Effectively, what this means is if this bank curve continued out in both directions until a full circle was made, the circular shape of the road would have a radius dimension of 76 meters all the way around. Thank you very much, everyone. In the next video, we're going to continue to apply some more Module 2 concepts to circular motion. Our focus will be on beginning to make calculations focused on energy and work, applying it to circular motion situations. Until then, have a good one.